We present AnyTop, a generative motion model that generates diverse motions conditioned on any character or topology. Most motion generation works exclusively handle single skeletons. Methods that handle multiple topologies are either limited to differences in bone proportions only, homeomorphic motions, or specific domains such as bipads. With just a skeleton definition as input, AnyTop generates diverse natural motion for various body parts and topologies. Of course, the skeleton motions drive the rigged characters. AnyTop is a diffusion model conditioned on an input skeletal structure and joint names to encourage semantic similarity between similar joints across the different characters. Before generation starts, an enrichment block first incorporates the skeletal features into the noised sample. The diffusion iterations are then processed by the skeletal temporal transformer encoder, applying attention on both the skeletal and temporal axes. In addition, skeletal attention is enriched with topological conditions, such as joint distances and adjacency relationships. Finally, the output is projected back to the motion representation dimensions and reconstructed into a motion sequence. Analyzing the results, we identify three types of generalization. In skeleton generalization is related to generating new motion variants that preserve the character's original motion motifs. The adapted SynMDM seen on the left cannot combine joints from different motions into the same frame. AnyTop combines a pecking motion with lifting a leg, drawn from different motions in the training set. In cross-skeleton generalization, characters learn from each other. On the upper right, the raptor stands on one leg, a non-raptorish motion that was probably learned from the flamingo. On the lower right, the chicken jumps in the air, although jumping does not exist in its training set. We believe this skill was learned from the ostrich. Unseen skeletal generalization extends to skeletal structures not encountered during training. The cat and Komodo dragon shown here were excluded from the training and generated by our model without seeing them. For comparison, we display motions generated by an adapted MDM. As can be seen, generation of unseen skeletons presents a significant challenge for a more naive solution. We analyze the deep features in our network and find that semantically similar parts are highly correlated across different characters. Note how left and right arms or forelimbs are nicely correlated, as well as legs and tails. Diff features also reflect temporal correspondence. Here, we extract features from the temporal attention maps of the monkey and search for their nearest neighbors in a crab and a lynx motions. We can see a correlation between relaxed frames in blue, transitional frames in green, and aggressive frames in pink for all sequences. Using k-means on our diff features, we demonstrate temporal segmentation. Each colored motion segment correlates with one k-means cluster. Again, note how semantically similar motions are nicely segmented together. We also enable editing operations. In in-betweening, the beginning and end of a motion sequence are given, and we synthesize the rest. We also support spatial or body part editing, where one part of the body is given and the other is generated. We compare AnyTop to MDM adapted for training on multiple skeletons. As can be seen, our results significantly outperform it in terms of quality, smoothness, and expressiveness. Thanks for your time.